Let me welcome our last speaker of the day, Ellie from Uber, who's going to talk about strings in iOS. All right, yeah, please, round of applause here.
Hi, everyone. My name is Ellie. I work at Uber in San Francisco. I'm in the mobile platform team. I work on iOS. We build tools and frameworks. One of the things I worked on before is a scalable code generator for mocks. It's called Macola, which is also open sourced. In this talk, I'd like to go over some of the pitfalls of Swift strings we had to deal with in our apps and tools, and what we learned from them, and what we did to optimize for correctness and performance. So Swift string, as we all know, is one of the most commonly used fundamental types in the standard library. It supports Unicode encoding, non-Latin languages like Arabic and East Asian languages, and our favorite emojis. So you can write a fun and expressive message like this greeting on the bottom, and have fun with it. In Swift string, an ASCII letter A, a family emoji, and a Latin letter E acute are all considered to be one character. This count value might be different in other languages like Java, C#, or Objective-C. If you look at the count value of the Unicode scalars, or the UTF-16, UTF-8 count values, the numbers are different. So for example, take a look at the emoji on the second row. The character count value is 1, but the Unicode scalar value, the count value is 7, and then there's 11 UTF-16 code units, and then 25 UTF-8 code units. And take a look at the character on the last row, which is E plus acute accent, combining accent, and the count value for that is 1. But there are 2 Unicode scalar counts, and 2 UTF-16 count, and then 2 UTF-8 code units. But Swift string goes to great lengths to support Unicode correctness, so all these characters are considered to be 1. It also performs equality checks, just as a user would perceive. So this Latin letter E acute has 2 forms of representation: a small letter E with a combining acute accent, and a single Latin letter. Both forms are considered equal, and the character count value for each is 1. So when different compositions form a semantically identical character, it's called canonical equivalence. And Swift string makes a lot of effort to satisfy the Unicode property. This user-perceived character is also known as an extended Grapheme cluster. A Grapheme cluster is a sequence of numerical values called code points. A code point is a unique number defined by the Unicode standard library for every character or symbol used in writing. It ranges from 0 to 1.1 million in decimal, which can be represented in 21 bits, which round up to 32 bits. A code point is a variable width, meaning it can have a varying number of code units. So take a look at this family emoji example. The character consists of 4 emojis: the father emoji and a joiner, the mother emoji and a joiner, girl emoji, a joiner, and then a boy emoji. Each emoji is mapped to a code point, which is then mapped to UTF-8 code units. Each emoji is mapped to this code point, which is then mapped to 4 UTF-8 code units, and the joiner in between is mapped to a code point, which is then mapped to 3 UTF-8 code units. So in total, there are 25 UTF-8 code units, even though there's only 1 character count. So how do these properties of Swift string affect us? At Uber, we have multiple apps: a rider app, driver app, Eats, Freight, and bike and scooter app. And they're deployed in multiple markets and localized in over 50 languages and locales. So the string correctness and safety are very important to us. Besides apps, we also built multiple developer tools, such as code generators for mocks, dependency injection, code cleanup, and so on. Our tools have to scan and parse our large code base, which has about 2 million lines of code in Swift. And they are run as part of a build system or at runtime. So the string's performance is very important to us. So if there are changes in Swift string, it can have big impact on our apps and tools. For example, the Swift 5 compiler shipped with several changes in string. The major change is the encoding scheme change from UTF-16 to UTF-8. This allowed unification in storage for more efficient memory management and better size and performance optimizations. So what does this mean to us? So while these changes are great and allow better size and optimizations, size and performance optimizations, we need to be on the lookout for potential regressions, especially if you're bridging with NSString, or if you're localizing strings, or if you have code relying on the old UTF-16 encoding scheme. And even though this change in compiler was introduced several months ago now, it's easy to overlook code that needs to be updated, especially if you have large code base like ours, or if you don't have good test coverage. This kind of overlooked code path can sometimes lead to incorrect behavior, or even worse, crashes, and that can be costly. In fact, we had a crash precisely because of this. After the compiler upgrade, our localized app started crashing, and we had to find out exactly what went wrong. In our driver app, we had a localized string like this. This was part of a pickup location string. The location is called Parko Honten in Japanese, which translates to Parko main branch. Parko is the name of a department store in downtown Tokyo. We were performing string manipulations, so we were storing indices. In this scenario, we had two strings, the name string, Parko, and then the branch string, Honten. The branch string had two characters, Honten. Our target character was the second character, and we stored an index for that character. Let's call that ID X. We then combined both strings. Let's call that combo. Then we used IDX and the combo string to recompute the index of that target character in that string. This calculated index was then used to apply different styling to that character. This line on the bottom used to work, but after the compiler upgrade, it started crashing. And of course, this happened during the pickup, so it caused a lot of cancellations, and that cost us a lot of money. So what's more confusing was that it worked with English strings. So what went wrong here? To find out, we first looked at what the stored index was. It's a struct containing raw bits. What are these raw bits? If you look at the dot comment of the string index type, it says it's a sequence of 64 bits, which contains position info and other metadata. The position is a 48-bit encoded offset into strings code units. What does this mean? If you look at the characters in the branch string closely, each one has 3 UTF-8 code units and 1 UTF-16 code unit. Index is an offset into these code units, represented in raw bits. Now, if you look at the distance between these two characters, it's 1 from the character view. And if you look at the distance from the UTF-16 view, the distance is also 1. But if you look at the UTF-8 view, the distance is 3, which makes sense. Now let's look at the combo string. It has two parts, the Parko, the name part, and then the branch, Honten, the second part. So as you can see, the second part has 3 UTF-8 code units and 1 UTF-16 code unit for each character, as we just saw. But the first part has 1 value for both UTF-8 and UTF-16 views. Now, if you pass in the indices using the branch string we just saw earlier, the start index and the IDX, to this combo string on the bottom, and try to compute the distance between the same 2 characters then, now the value is different. It's no longer 1, it's 3, which was the distance value from the UTF-8 view in the branch string. So before the compiler upgrade, this value was 1 because the default encoding scheme was UTF-16. But because it changed to UTF-8, now the value is 3. If we print where the stored index points to in the combo string, it's indeed the 3rd character. Trying to get the character at that index will return an incorrect value. And if we increment the offset from that point on, it'll crash even before we get to the end of the string, with an index out of bounds error. So this shows that we were using the stored index incorrectly. But because the previous compiler used the UTF-16 scheme by default, this buggy code still worked most of the time. So what's the correct way then? The correct way is not to use an index from another string, but to compute from the start of the new string to get the target index. And for the offset, use an added string count and the character distance, as shown on the bottom line. Lesson learned here is that if we have code relying on the old UTF-16 encoding scheme, we should actively audit it and update it. One way to do that is to add tests for index calculations or string manipulation code with various inputs, including non-ASCII strings and localized strings, so we can catch bugs earlier on and avoid crashes. Next, let's move on to string performance. We have a greeting. Hi family, it's sunny on this palm tree island. We want to know the index of the sun emoji, so we can change it to, let's say, a rain emoji in case it starts raining. This is the 12th character, so we pass in that value to this index API to get the sun emoji index. The preceding characters have variable width, for example, the family emoji. So we can perform random access to look up the 12th character. We have to perform a linear scan, and this is O(when). Let's say we want to write a wrapper function that returns a substring given an integer position and length. In order to perform a lookup, we first need to create indices with these values. We first calculate the index for the position starting from the beginning and walk over the length of the position. Let's call that begin index. Then we calculate the next index for the position plus length, again starting from the beginning, and let's call that end index. Each one is O(when). If that gets called a lot, it can slow things down. In fact, we had a function just like this, and it became a bottleneck in one of our tools. So we had to optimize it. So we first converted the input string to the UTF-8 view because we found that performing on that view was faster. Then after calculating the begin index, we use that to compute the next index to reduce the amount of walks. Since we were reusing the begin index in the same string, it was safe to do so, and we saw some improvements in the speed. But it was still not fast enough. It's still O(when) because it still needs to calculate the first index. And even with the UTF-8 view, it still performed the linear scan. So then we looked at other ways to optimize. We looked at C-string, but the APIs were cumbersome and involved calculating pointers by hand, which could get tricky. And we looked at NSstring. The lookup is fast, but involved conversions between UTF-16 and UTF-8, and also Objective-C bridging overhead. We then looked at using data. Unlike C-strings, the APIs are easy to use. We didn't have to calculate pointers or perform bit shifts by hand. Data also conforms to the collection protocol, so we could use functions like split, subdata, starts with, range of data, and so on. And because it supports random access, lookup is fast, and we could use integer indices. And it's easy to convert to and from string, which is very useful. So we could perform all the expensive computations on data first, and then convert to Swift string at the very end. Using data, we could rewrite the extract function like this. Now all of these index creation lines are gone, and we can directly pass in the range for a lookup, and it's of 1. We benchmarked the extract function using string and using data, and here are the results we got. The input was 3,000 lines of code with various offsets and lengths averaging 150 bytes. It was called about 10,000 times and run on the latest Swift compiler. This simulates the actual environment using one of our tools. And as you can see, the one using data was significantly faster. There are a few constraints though. Because data is byte buffer, the inner values for the offsets and lengths have to represent bytes. And if you want to perform operations like split data, you need to make sure that the separator character is not part of a composed character. Otherwise, it can return unexpected values. And if you have control over your input space, perhaps you can rearrange it to fit within these constraints, so you can still take advantage of the performance benefits. This is not to say you shouldn't use Swift string at all. Not everybody works on performance-intensive code using Swift string. And you might want to keep Swift string as is and improve the speed in a few spots here and there. If that's the case, I would still like to recommend profiling APIs, string APIs, so you can still gain some performance benefits. So as we saw with the index APIs earlier, just because you're using the standard library function doesn't mean they're all optimized. There's a lot going on under the hood that we don't know about. So benchmarking different but equivalent functions can yield surprising results. Profiling these APIs can help you choose faster operations to achieve the same functionality. So let's take a look at a tokenizing operation. We can use a split with a separator function or a component separated by to achieve the same thing. The only difference is the split function returns the substring types instead of the string type. We benchmark the two functions using an input string like this. It's an ASCII text containing 1,000 characters in total, including 150 spaces and 10 new lines. When we benchmarked with a space separator, the split function was indeed faster. We ran it about 200,000 times on the latest Swift compiler to simulate the actual setup environment used in one of our tools. Given the input string with 1,000 characters and using a space separator, the output produced was 150 tokens. The split function took about 10 seconds, while the component function took about 15 seconds. We converted the results of the split function from substring to string type, but even then the numbers were similar. What if we used a different separator this time? For example, a new line separator. This time, the components function is a lot faster. while the split function still took about the same amount of time as before. Note that this time the output is 10 tokens. So why are there these discrepancies? Let's find out by first profiling the components function with the two separators. The result on the left is with the new line separator. The result on the right is with the space separator. The left one returns 10 tokens and takes about 3 seconds, while the one on the right returns 150 tokens and takes about 5 times as long. So as you can see in the call tree, this is an NSString API. The first highlight function is a cfstring function, which is called by NSString range of string function. This is used to find tokens to be separated. The next highlighted function is new substring with range function, which creates NSString copies for the tokens. And the last highlighted portion is a protocol method used to convert those copies from NSString to SwiftString. And these are called in a loop. As you can see, each call on the right takes longer. Let's have a closer look. The range of string function calls an internal cfstring function called cfstring bind with options and locale. This makes use of cfstring inline buffers and tagged pointer strings, which are optimized for fast access. So when there are fewer tokens to separate, it can just perform the fast walk and just return the results for those few tokens found. But when there are a higher number of tokens, it now needs to spend more time in that new substring with range call, which creates substrings for the tokens and converting them to Swift strings. That involves calling methods on the Objective-C bridgeable protocol. And this involves dynamic dispatch, which is expensive. As you can see on the last row of this table, it spends about 7 seconds on the protocol method when a space separator is used, while it takes about 0.3 seconds with a new line separator. So if the number of tokens increases, you can see how it can become a bottleneck quickly. Okay, so what about the split function? How come calling that function showed more or less the same number with both separators? Let's profile again. The result on the right is the split function result. And for comparison, we have the components function result on the left. They both use a new line separator. The split function takes about 10 seconds, 3 times longer than the components function. The split function spends most of time calculating string indices. Once again, the culprit is the string index handling. This index update function is called in a loop and makes several internal calls, such as character stride, scalar align, and so on. In contrast, the function on the left is faster, even though it also walks over the entire string. But as we just saw earlier, this makes use of optimized structures and APIs for fast access. So the question is then, how come the one on the right doesn't make the same optimized calls? The input is just an ASCII string. So why is it calling all those internal functions that are slow? Well, this is when the Swift GitHub site can become useful. You can look up the implementations. So we went to the Swift GitHub site and searched for the function, and this is what we found. So as we just saw in the call tree, it does indeed make those character stride and scalar align calls. But notice on the top, there's a to-do line. It says it still needs to add a fast path for an ASCII input string. So there we have an answer. This is why it's slow. They haven't added an optimization path yet. So will Apple implement this soon? Who knows? So until they do it though, we'll have to work around this by perhaps rewriting this function or its color function with our own optimizations. If we plot the results of the two functions together, the split function and the components function, this is the graph we get. The yellow line maps to the components function, and the blue line maps to the split function. As you can see, when there are fewer tokens, the components function is faster. But after a certain threshold, split function is faster because it doesn't have to allocate as much memory and perform the expensive protocol method dispatch calls. So what does this tell us then? What can we do with all this information? This kind of analysis can give us a better idea about how and where we can optimize by choosing more efficient functions or rewriting slow code path with our own optimizations. Now let's go back to the ASCII text we saw earlier. It's too plain, so let's add emojis. Will it change anything? Will it make it faster or slower, or will it be about the same? Yes. So let's find out more details though. To start, let's just add one emoji and keep the new line character as a separator. With one emoji added, we found that the split function, again, took about the same 10 seconds, while the components function gave different results. Profiling the function showed that it makes different calls depending on the input contents. It first performs a runtime check to see what the backing class is for the input string. When the input contains a non-ASCII character, even one emoji, it uses what's called shared string storage, a type used for large strings which don't have fast access to contiguous UTF-8 code units. It creates a buffer, then copies UTF-16 contents into it, which involves transcoding from UTF-8 to UTF-16, and that involves a linear walk. It then calls the getIndex function, which involves more calculations on a non-ASCII input string. So overall, this adds more overhead and makes it slower, even though we only added one emoji. And the results are similar whether you add one emoji or multiple emojis. So how do string APIs then decide whether to call a fast optimized calls or a slower function calls? When a string instance is created, it creates a backing string object with this memory layout on the top. The most significant 4 bits are what's called discriminator bits, and the remaining bits are used for the object address. The discriminator bits contain information such as whether it's an ASCII string, whether it's abridged, whether it's a small or a large string, or whether it's an NS string. For small strings containing up to 15 UTF-8 code units, it uses a struct called a small string for efficiency. But for large strings, it stores this count and flags info on the bottom. It contains the count value of the code units, as you can see at the end, and the flags indicating whether it's an ASCII string, large native string, or if it has contiguous UTF-8 code units for fast access, and so on. These flags and discriminator bits are then combined to determine whether to call faster functions or slower functions. Keep in mind, though, these flags are best estimates, so it's possible they are not always up to date. They are set when the string is initialized if it can perform a quick check. These are then lazily updated when the string is mutated via insert, remove, replace, and so on. Also, even if there are these flags, not every code path uses them, as we saw with the index API that has the to-do line earlier. This gives us a better idea about why string behaves in one way or another. it's useful to profile these APIs and check out the internal implementations. This can help us understand the string behavior and optimize our code better. This doesn't mean you have to optimize everywhere, though. Not everybody works on performance-sensitive code with SwiftString, so if you're not working on them, you can probably use SwiftString as is. But if you are, it would be beneficial to benchmark and optimize them. Putting everything together, SwiftString goes to great lengths to support Unicode correctness and various languages and emojis, but it comes at a price. The interface is more cumbersome, the APIs can be misused, which can lead to incorrect behavior or crashes, and it has performance implications. So I'd like to reiterate that it's important to test correctness, and one way to do that is to add non-ASCII strings to your tests and make sure to test index handling and string manipulation code. And be sure to profile string APIs with various input contents and parameters and optimize them for performance hotpaths. This way, we can safeguard ourselves against some of the pitfalls of Swift strings for both correctness and performance perspectives. That's the end of my talk. Thank you.